Hey everyone, my name is Asam Ghazi, and today I'll be discussing our group's work on studying how vagus nerve stimulation delivered non-invasively at the neck affects the various phases of breathing, namely inhalation and exhalation in the context of traumatic stress. So we'll start with a simple enough question. When you feel stressed, what do you do to calm yourself down? Well, I'm sure a few of y'all may have thought some form of deep breathing, and the American Institute of Stress would agree with you, where they have a specific page, for example, devoted to how proper breathing can help reduce stress. And from their tips and reminders, one in particular stood out to me. Always take longer to exhale, twice the time you spend breathing in. I wondered, as someone who studies stress, why? Well, when you take a look at the underlying physiology of breathing in the vagus nerve activity or vagal tone, their recommendation makes sense. When you inhale air, what actually happens is that vagal tone decreases. But when you exhale, on the flip side, vagal tone increases. And the vagus nerve, as part of the parasympathetic nervous system or the rest and digest system, counteracts those feelings of fight or flight you feel due to the sympathetic nervous system activity accompanying distress. And that's why potentially longer exhalations could be used as a way to hack the vagus nerve, where you leverage this relationship to reduce distress in the moment. For those that study vagus nerve stimulation, we know another way to hack the vagus nerve, specifically electrically. And so I wondered, what have we studied in the vagus nerve stimulation literature to understand better this relationship between the phases of breathing and stimulation? Well, in recent work by Dr. Vitaly Napido's group, they studied a group of subjects where they compared three forms of stimulation, namely the first, transcutaneous auricular vagus nerve stimulation, delivered only during inhalation, respiratory gated auricular vagus nerve stimulation, or RAVENS for short. The same Raven style stimulation, but only delivered during exhalation. And then a sham stimulation delivered at the earlobe during exhalation. And what they find when comparing the three is that stimulation during exhalation actually enhances the therapeutic tVNS effects. So what this sort of implies when you take a step back is that, okay, exhalation has some effect on tVNS effects, namely it enhances those. So what if instead of respiratory gating the stimulation, you delivered it continuously and studied the converse, namely, would tVNS itself affect spontaneous breathing sort of exhalation time? Because if it were to increase this exhalation time, mind you, recall, exhalation reduces stress. When you do longer exhalations during proper breathing, you can reduce the stress, which could imply potentially that tVNS could be used as a subconscious promoter of stress reduction. Well, in prior work, what we find is that our group studied stimulation delivered cervically, no respiratory gating, an active and a sham group. So active TCVNS versus sham stimulation. What we find is that respiration rate was actually decreased significantly by the active stimulation comparison to sham, but the inspiration and expiration phases were not studied. So we set out to do so in this paper. So what are we looking at here? Well, the specific system that we're investigating involves this cranial nerve, this vagus nerve, and its connection directly from the brainstem to the end effector organs. And when you stimulate this nerve, it's believed to occur where afferent signaling is the result, followed by efferent modulation of the lungs and the heart, along with other organs, in a therapeutic manner. Now, how can we pick up these sorts of effects? How can we sense these effects? Well, we can use non-invasive physiological sensing. Namely, we can collect the electrocardiogram signal along with the respiratory effort signal measured using thoracic belt. And what we did was we studied 26 non-PTSD subjects with a history of psychological trauma, so traumatic scripts would induce stress, and we studied them in a double-blind sham-controlled setting where we compared an active stimulation to a sham stimulation, but neither the researcher nor the subject knew at any given time whether they were receiving active or sham. And so we set out using these signals to investigate whether the specific phases of inspiration and expiration were affected in any significant way by active stimulation in comparison to sham. Seems simple enough to do just that, right? But those who have processed these sorts of signals understand that the respiratory effort signal, along with other respiration signals, can be deteriorated by artifacts. Take a look at this example, where we show this specific data sets as an example, this specific data set as an example because it has spirometry as a baseline, as a gold standard. And what we see is that during this specific window, subject is clearly breathing, but this is missed by the respiratory effort belt signal, likely because of loosening. How do we circumvent these artifacts during our analysis to maintain legitimacy? Well, you can use things like respiration quality indexing, these sorts of techniques, to actually classify windows as being of sufficient or insufficient quality. But you can imagine if you're simply classifying these windows as insufficient quality, you might lose quite a bit of data if artifacts are prevalent. How can we replace these windows of data? Well, remember that we're sensing the ECG, and from the ECG, you can actually derive respiration signals. Namely, there's a baseline wander signal, also known as a respiration-induced intensity variation of the ECG signal, along with an amplitude modulation during breathing of the ECG signal, also known as the respiration-induced amplitude variation signal. And what we find in this specific example is those two signals maintain sufficient quality even though the respiratory effort belt deteriorated. And this actually inspired our overall signal processing approach, taking it one signal at a time to come with a better understanding, a consensus, so we're all on the same page. The ECG is first bandpass filtered, followed by signal quality assessment using the approach of Johnson and colleagues published in 2015. This is followed by the classical Pan-Tompkins approach for R peak detection, and then R to R intervals, or for short, RR intervals, are extracted, and then outlier removal plus minus 4 standard deviation is applied to arrive at a clean set of RR intervals. This clean set of RR intervals, along with the raw ECG signal, is then used to extract RI-IV and RI-AV, which then can be used to supplement the respiratory effort belt signal. All three of these signals are bandpass filtered within the range of plausible respiratory frequencies, and then fused on a feature level. What do I mean by feature level? Well, we take these three signals, and one path of this low-level signal processing diagram, it's focused on using adaptive thresholding to extract inter-breath intervals and onsets. But we don't just use all three in some haphazard manner. Rather, we take these same three signals and feed them through respiration quality indexing approaches of Berenkot et al., published in 2018, to then take these 16-second windows of data and rank the signals in terms of their quality, taking always the features corresponding to the signal of highest quality, as long as at least one of the signals met a minimum quality threshold. After that, the rest is based on outlier removal, outlier flagging, and then removal, and then the final set of features is extracted, namely inspiration time, expiration time, and of course respiration rate was studied in prior work. If any of that was confusing in any way and you need some more low-level details, not to worry, in an upcoming journal publication, we plan to actually share our source code in implementing this signal processing pipeline. So what do we actually find? What do we find when we study inspiration time, expiration time, how is affected by vagus nerve stimulation? Well, when we compare active and sham, the first finding that we see is that yes, tVNS does in fact lengthen exhalation time in comparison to sham, and this remains significant even after a conservative Bonferroni correction. But what makes this result even more interesting is that inspiration time is not significantly affected. And what we find is that when we look at the ratio, inspiration time to expiration time ratio, this result is further corroborated by the fact that there's a decrease in the active group in comparison to sham, meaning that the expiration time was lengthened in comparison to inspiration time. So what do these results suggest? Well, just as exhalation enhances tVNS effects enhance exhalation. And this intriguingly could imply a positive feedback effect that can help these sort of therapeutic effects of vagus nerve stimulation linger on post-stimulation, given the beneficial counteracting of stress effects produced by exhalation, lengthened exhalation. Along with that, if VNS can subconsciously lengthen this exhalation, therapists could potentially use tVNS as a method to augment their breathing retraining therapies. And of course, expiration time could also be used post-stimulation as a biomarker to ensure the elicited effects have occurred. Where to next? What do we study next? Well, these findings should certainly be validated in a larger sample, and potentially disease populations such as PTSD and panic disorder where neurorespiratory couplings are compromised should also be studied. Thank you all for your time, and I look forward to your questions.